of mine about leaves. The leaf is one of the most amazing evolutionary innovations, and we don't think about it. It determines the way the world looks, it feeds us, it does all sorts of wonderful things, but nobody thinks about leaves. And so my goal in this presentation is to offer some ways of thinking about leaves and why they're so variable and wonderful. And there's several ways I could have approached this. One is the incredible biochemistry that a leaf is, and taking in a little bit of carbon dioxide, water, and a few nutrients that can make everything. That's a biochemical wonder. For that, you need a biochemist, not an ecologist. I'm an ecologist, so it seemed more useful to look at how it is that leaves, all of which are doing the same thing, are so incredibly variable. And why is this tapestry such a wonderful thing? And that's what I want to explore, and we'll see if you find out that this was useful. If it wasn't, you have some opportunity in Q&A to let me know. So with that, let's have the video. It's my pleasure to talk to you this afternoon about leaves. Leaves are a wonderful evolutionary invention, and they're all doing the same thing. They take carbon dioxide from the air and powered by sunlight, and they take up from the earth water and all the varied nutrients they need, and they make sugars, and from that the plant makes everything else it needs. So all leaves are doing exactly that same thing. Then why are they so varied? Why isn't there some super leaf that sort of triumphs over everything else? And I want to explore with you some thinking tools that enable you to maybe imagine and comprehend why leaves are so marvelously varied as they are. But let's back up a little bit before we get into the details. When plants lived and evolved in the ocean, in the water, there weren't any leaves because there wasn't any need for anything like a leaf. The plant was just bathed in the ocean water that had all the nutrients, and the sunlight was right there. And so you had very simple plants that didn't have any conducting systems and special tissues, all the same. So that's why these huge kelps, the kelp forests, it's a simple layer. Every cell is so photosynthetic. They can grow at tremendous rates, and they make marvelous forests, but they don't have anything like a leaf. But when the plants invaded and started to conquer the land, then this was a very different and very hostile environment than the one that they had been involved in, because now the air still provides the carbon dioxide, and the sunlight comes from there, but the plant now has to get everything else, the water and all the nutrients from the soil. So it needs to develop some sort of a system for getting things from different environments and moving things around. And so then plants started to develop some little systems to do that. And the first plants were like these mosses, very, very simple. They can't conduct anything around. Mosses are marvelous and beautiful. They never get very big. They don't have any systems to transport things around them, have anything like a leaf, and they can just dry up and sit around for a long time. If it gets wet again, then they can brighten up and start photosynthesizing again. So for a long time on land, this is what the plants were like. And mosses are very successful now, but they're all small, and they don't have any system for carrying things around. So when plants started to grow and get a bit bigger, they had to develop these systems for a vascular system for moving stuff around, because there's a lot of tissues that are photosynthesizing. The roots are getting stuff, but the leaves have to feed feed the roots, the leaves have to feed the stem, and when we're making flowers and fruits, the leaves have to make support all of those things. So the plant gets very complicated, and has to have a system for moving things around. And so that's when we started getting unique things like leaves. There's a part of the plant that's devoted to capturing all the energy from the sunlight and making sugars, and from that everything else. So that's how leaves start. And then let's proceed by, first let's just talk about making a leaf. And here's a little diagram here. You can see I'm not an artist. And this little diagram, and this is zero energy, gain or loss. Here's gain, here's loss, and this is time over here. And so let's imagine the plant starts to produce a leaf and goes into energy debt because it expends energy to make the leaf and all its parts. And the leaf is, and then at some point at the bottom, the leaf starts photosynthesizing, starts to pay back, and up at some point, the leaf has paid back, and then we have profit going up here. And if we have a tougher leaf, it takes more to make it, and so we go deeper into debt, and it's longer before it starts paying off, and a longer time before it gets having paid the investment, and then a longer time before it is making the profit. And so this has a lot to do with the kind of leaves that we see. If a leaf is being made, like these maple leaves, for just a one growing season, they're pretty flimsy. It doesn't take much to make them. They hang there, and when they fall down, there isn't all that much. These are the cheap leaves, like the first little curve on that diagram I showed you. But it takes a lot longer to make one of these, a leaf like this. What you find is that these kinds of leaves are made to last multiple years. And this leaf is a magnolia leaf, and it's going to last quite a few years. And so it's a long time before it pays off, but it's tough so that it can withstand multiple seasons and stuff. But it's going to be around and paying off for quite a few years. And the same is true of conifers. These conifers, each year is a little growth here, and so these needles may last up until 7 or 8 years. And so they're made pretty tough, but we also have conifers that are deciduous, and there's a lot of them down in Freeway Park, the larches, and I just picked these at the same time. Most of these are already shriveled up and looking pretty sad. And so these are conifer leaves that are made for just one season only. And we have 2 native species of larches in the mountains of Washington. And also then there's some native conifers in the east that are deciduous. Those of you from the northeast may know the tamarack, which is common in the bogs. And from the southeast, there's the bald cypress. It's called bald because it drops its leaves in the winter. And again, these just like, this is the difference between a multi-season leaf and a one-season leaf. So a lot of the differences between the leaves can be explained by how long a time is the leaf being made to last. And a lot of the differences, nothing like this is made for a single season, and nothing like this is made to last a lot of seasons. So that's one thing that contributes to the differences in leaves. Another relates to the sunlight. And here's a terrible diagram, but because it's all out of scale, but the scale scale is the difference from the sun is not a point source of light. And here's the sun, and here's the leaf, and this distance, of course, is 93 million miles. This is all out of scale. But because the sun is not a point source of light, shadows disappear behind the leaf, and a leaf, this is the leaf, this little dark thing is a leaf there, and I've depicted the shadow sort of as a cone decreasing behind the leaf, and at 108 times the diameter of the leaf, the shadow disappears. And so this simple fact, and that's just geometry, no theory there, that the sun is big enough not to be a point source of light, that affects a lot about how leaves are depicted. So here I have two leaves from the same red oak tree here, and you can see that they're all the same tree, so they're not, this is not due to any genetic differences here, but this happens to be a leaf from the top of the tree, and this is one from the bottom. And so what's the adaptive significance of that? Well, the diameter d of the leaf is nothing to do with how wide the leaf goes, but how big a circle you can inscribe within the leaf. Because otherwise, the sun comes coming through. So this circle I drew there is the effective diameter of this leaf, and this is the effective diameter of this leaf. It's quite a bit bigger. So the shadow disappears quickly behind this leaf, and much more slowly behind this one. So what in fact is happening, since the rate of photosynthesis peaks out at about a quarter of full sunlight. So even though a bunch of leaves like this up there will cut out part of the sun, they won't make any shadow. So the next a bunch of leaves lower down can still photosynthesize at the most rapid rate possible. So you can stack a number of leaves. So trees that are growing, adapted to grow out in the open, can make multiple layers, and they can look very open and filmy, like these maples, because these leaves are highly incised, and they cast rather short shadows. So a part of the difference between the leaf shapes then, and some of it can do it entirely. This has nothing to do with genes, this difference. This is the same oak tree. The developmental system for a leaf is triggered by how much light the leaf is getting when it actually is being formed. So the sun is not a point source, but also it's got some peculiar properties. The sunlight can't be depleted because it is renewed at the fastest rate that is known on Earth. And the fastest rate that we're told by the physicists is theoretically possible, namely it's renewed at the speed of light. So, but the sun doesn't always shine. It does go down at night, and there's no sunlight at night. And the sun is moving across the sky, and so how the leaves are going to be intercepting the sunlight depends upon the time of day. And so this branch is designed to be out in the open, and as the sun is passing over about any time during the day, there'll be about the same number of leaves opposed to the sun. But if we have them arranged flat, during early and late in the day, this branch will not intercept so much light, but in the middle of the day when the sun is coming straight down, it doesn't cast much of a shadow. So we find in a lot of plants that the arrangement of the leaf depends on whether the plant is growing in the open and it's going to get sun during the entire day, or whether it's only going to get sun a little bit during the middle of the day down in the shade, and all leaves like that are going to be flat. Because early and late in the day, the sun is also these kinds of leaves are often likely to be fairly flat in their orientation, and they're designed to pick up the sun at any time during the day. So not only the sun has the properties, but it moves around. And there are actually plants that move their leaves to be able to face the sun during any time during the day. But then there are also plants growing in the open where the middle of the day is really very hot. And the optimal way is just to have leaves that hang. If you've been to Australia, one of the characteristic things of eucalyptus leaves is they all hang. So they're picking up light early in the morning and late in the afternoon, in the middle of the day. They're just casting almost no shadow at all. They're not overheating. And so that arrangement is related to how much heat load the plant's going to receive. And also this, excuse me, these leaves, these maple leaves, will dissipate heat pretty rapidly. They can get rid of it. This leaf is going to get hot. And so part of the difference we see in the structure of leaves, it depends upon whether they're growing in the open, whether they're in the hot climate, and how dry it is. Another feature that's different is that there are lots of plants that have what we call compound leaves. And this is a compound leaf. This is one leaf, but these are leaflets. And we know that is different because it's the attachment of the leaf to the branches here, and this falls as a unit. So what the rachis here of this compound leaf is a very cheap annual branch. So the plant can grow a lot of that out, get a lot of leaf structure out during one season, and the branches that supporting the leaves is pretty cheap. It doesn't take much to, and when it dies down, there's not much loss. And that kind of compound leaf situation becomes increasingly common in arid or semi-arid places, because that's true, for example, if you've been to Africa, all the acacias have compound leaves, and these are trees that aren't going to grow much, but each year they can put out a lot of leaves and do a lot of photosynthesizing. They're doing it on these really cheap branches that fall, and so a picture you would take of an African savanna, probably 50 years later, look almost like it does the year before, and it looks like, how could they be putting out new leaves and doing a lot of photosynthesizing? They put them out with cheap compound leaves, and that enables them to leaf out, do a lot of photosynthesizing when it's wet, and when they drop, it's very cheap to support for the leaves. It's a rachis, and it's not nearly as strong and complex as making a branch like this. This is tougher stuff. So that another variation in leaves is whether they're simple, like these. That's one leaf, or whether they're compound, and this is also one leaf. So this is a couple of ideas about why leaves are not, even though they're doing the same thing, they're not doing them in the same kind of environment. They're not built to last the same amount of time. They're not related whether the sun is going to be hot or not, and whether or not that they're big enough to be able to stack leaves and put these one on top of the other, so this one is not, the shadow from this leaf is going to disappear much faster than the shadow from this leaf. So those are several of the reasons why, although all these are they're all doing the same thing, they're very different. And I want to mention one more thing that is important, and it takes a little bit, I have to explain a little bit about plant anatomy. The main vascular plants, the ones that are all around us, fall into two main groups. They're called the monocots and the dicots. that's what's in the seed. That's what's the leaf that's packed and in the seed, and that's got all the energy that's going to get the new plant going until it's on its own. And the dicots have two of these. And you can see this with when we have split pea soup. You got the pea that's got two things, and those are two cotyledons. And when it comes out of the ground, they're going to be two fat leaves, and that supports the growth until the plant can get on its own. So those are the dicots, and you can see this with a peanut and a half. So it's easy to see. And the dicots, most of the plants we see are dicots, and they grow like we think woody plants. Those that are woody grow like we think woody plants should grow, namely they have growth rings. So they can get fatter and fatter as they get older. And we can tell how old they are by putting a little core in and seeing how many annual growth rings there are. And we can age the tree. And there's a recent issue of Science just came up with there's a reporting on an article that there's an alerce, a big coniferous tree in Chile, that they think is something like 1,400 years old, and they're determining that by getting a core and getting the growth rings. The monocots, on the other hand, are built very, very differently. Well, also the dicots, the flowers the familiar flowers are either in parts of 4 or 5. We look at them and they're four petals or 5 petals. The monocots now are very different. They are built entirely differently. And so they have only one seed leaf. When you plant a corn plant, for example, grasses are monocots. The leaf comes up and there's just one seed leaf, fat, and that supports the rest of what comes up. So the monocots also are different in that they can't add growth rings. They don't have the ability to do this. So monocots are very poor at making trees. So the vast majority of the monocots that we enjoy are herbaceous plants, and they're wonderful for flowering because they aren't spending a lot of energy making wood, which the only purpose of wood is to support leaves. Wood is a drain. It's the price the plant pays for getting the leaf up a little higher. And the only reason for getting the leaf up higher is that you can get above somebody else that's competing with you. So almost all of the vertical growth of plants relates to getting higher above somebody else who's going to shade you. And that's why when we grow for cultivating stuff, we grow low stature stuff that doesn't make any wood because we keep the shade away by plowing and weeding. And so agriculture is based almost entirely on herbaceous annual plants, and particularly grasses. About 3/4 of all of the energy that humans globally consume comes from 3 annual grasses: corn, wheat, and rice. They're incredibly productive. We don't eat this. We don't eat the leaves of any of those because grass leaves are very heavily defended, as I'll explain in a minute. But we can get this incredible productivity out because virtually all of the plant is photosynthetic. And that's why if you go to eastern Washington in the apple country, they're replacing apple trees as they get old, and they're replacing them with dwarfs that don't get more than about 6 feet tall. They're easier to prune, but you can plant a lot of them, and you actually get a higher yield of apples from an acre from dwarf plants than from taller ones, because you're spending less energy on making wood, which doesn't produce anything. All it does is hold the leaves up. So if you haven't noticed it yet, next time you go into eastern Washington, go through apple country, notice that almost all the new apples and pears as well that are grown, they're dwarfs. They just don't get big. And in fact, the only reason for getting big is to get higher up from that somebody else is going to shade you. And what we do when we do agriculture is we prevent anything else from doing this. But the monocots also cannot form these growth rings. And so they're nearly all herbaceous, and they put all their energy into flowers, and they're wonderful. The lilies, the orchids, just wonderful. And a lot of the spring flowers are monocots, but there are far fewer major groupings of plants in the monocots, but two of the most speciose families of plants are monocots, the grasses and the orchids. And another thing that's different about monocots is that the flowers, rather than being 4 or 5 in units, they're based on a structure of 3. There's you see here's the two things and this thing coming down the middle, and this is the same structure you find in an orchid going wild. So monocot flowers are based on variations on a theme of 3, and the dicots are 4 or 5. Monocots also have different leaves. They have parallel veins. You see the veins are all going in the same direction here, unlike the highly reticulated veins that you see here. I'm not sure they're not going to show up very well, but the monocot leaves are just all parallel veins. These are tulip leaves. So they're all the veins going in the same direction. And the crowning glory, so to speak, with respect to human beings of the monocots is grass. And the grasses, there's one exception I'll just mention that we give out because basically grasses are like this, and just the leaves are blowing in the wind. And then there's the fruits on the top, which is what we eat, because grass leaves are heavily defended with silica. They're very hard and tough, and animals that graze on these, their teeth wear down very fast. And so along with the evolution of grass is the evolution of the high crowns, the continuously growing molars of animals like horses and cows that eat the grass, because the silicon keeps wearing the teeth down. And so, and that's why, of course, the phrase is don't look a good horse in the mouth. So if somebody's giving you a horse, you don't want to insult them by looking in the mouth. But if you're buying a horse, that's the first place you should look. See what the molars are like, and that'll let you know that somebody's trying to pass off an old nanny on you that is well past its prime, because otherwise you'll not be able to see it. So the grasses are heavily, unlike a lot of the other plants, are not defended chemically, but defended physically with a lot of, so stuff really wears down. Also, another feature of grasses that's so interesting is that the growing point of the grasses is down at the bottom. When the grasses are growing from here, this is not actually actively growing up here. So unlike all these dicots I've been showing you, the growth tips are out on the top. So if you mow them down, you hit and destroy the growing tips of the leaves. You don't do that. The grass is growing down from the bottom up here, which is of course why when you mow your lawn, you don't kill the grass. As a matter of fact, you stimulate growth because you open up get to let more sunlight come in, so the grasses down there at the bottom will grow more faster. So the grasses, in a sense, are designed to be grazed. And when you get to a place like the Serengeti in Africa, that tremendous productivity of the system is enhanced by all the big mammals eating the grass down, and it stimulates more, and you get a lot more grass growing in a year if the things are being grazed than if this apart and it stops growing. So human being, our evolution is really tied up with the evolution of annual grasses. And that's, as I mentioned, most of what we eat is the seeds of annual grasses. And a lot of the way the mammals are built is dependent upon the grasses and the particular nature of grasses that they grow from the bottom up rather than having the growth tips outside. So, as I mentioned, monocots then, they don't have growth rings. So they're very bad at making trees, and nearly all of them are like our irises and tulips and orchids and grasses are non-woody. They don't make any wood because the monocot growth form doesn't work very well to make wood. And there's one, so almost all of our monocot friends are herbaceous. That is, they don't have any wood, make any wood at all. And they die back down in the winter. But there's one family of monocot trees that is just stunningly different from all other trees because they're growing differently because they're monocots, and that's the palms. Palms are monocots. It's the only big monocot trees that there are around, and because palms are monocots, they can't grow by adding growth rings. So a palm comes out of the ground at the diameter it's going to be, and it goes up, and if you notice palm trees, you know that that's the same diameter all the way up. They're not tapered like these others. And they don't have this inside, so it's very different. So you can eat, and we do eat heart of palm. We're never going to eat heart of maple or heart of oak. The inside there is a pretty tough stuff. The inside of palm, there's no growth rings, and it's a totally different thing. Palms have solved the problem of being a tree while being a monocot. They have no branches, with one exception, and the leaves are put out entirely on the top. And as the palm grows, it just has leaves only right at the upper tip. And this turns out to be highly advantageous in hurricane areas. Palms become very important where there are hurricanes. So what happens is the wind gets stronger and stronger, the leaves just detach. And I've been into a forest in Puerto Rico after the hurricane had come through, and it looks like you got a lot of dead palms there. Well, 6 months later, they're putting out new leaves so that it doesn't knock them over. So palms are absolutely amazing. They're not built like any other trees that we have, and they're a triumph of having figured out how to be a tree beside being a monocot. So, leaves are different in many ways because even though they're fundamentally doing the same thing, they're doing it in different ways, in different environments faced with so these grass leaves blowing in the wind have transformed the earth and transformed human culture, and it's wonderful, though we're never going to do the same with them. So I hope I've given you some thinking tools that enable you to understand that even though these leaves are doing the same thing, there are reasons why they are so different. And maybe I've given you some thinking tools that will help you understand and able to think about why it is that this tree is different than this tree. Take a look at it, what you should look for to try to get clues as to what's going on. And as far as if you don't believe this, I invite you to go out and take some leaves that are very tiny or something like this. Go out on a sunny day on a sidewalk out here and start with a branch right close to the ground and just raise it up And look at the shadow as you're doing it. You're watching the shadow disappear. You got to do with small leaves and things. So what you're doing is, as you move that up, you're going down this triangle, and you can see that the shadow getting very, very fuzzy and weaker. And you can actually see it. So if you don't believe this diagram, which is grossly out of scale, of course, you can see that effect of the shadow disappearing as a cone behind the leaf by just moving it yourself from the ground up, and in a sense you're just moving along this as you move it away from the ground. So that's a fun thing to do, and you can see that any sunny day, and we do have them here, and a nice clear background. So leaves are fun. I'm not giving you every reason why they're different, but I've given you the fundamental things that drive this. And I hope you enjoy going and looking at leaves in the future and knowing why part of the answer is why they're so varied is blowing in the wind. Thank you. Thank you. I should make a couple comments before we go into Q&A. I used some evolutionary shorthand, therefore there was a need and therefore they did this. So evolution has no hindsight, it's just a variation occurring, and under the new circumstances, new variants are favored. So there's no thinking that the plants are knowing what they're doing. In fact, one of the most depressing things about plants is that they show us that you don't have to have any brains at all to succeed. And as those of us that tend to be so brain-oriented, it's sort of depressing that the most successful organisms on Earth have no brains whatsoever. So I use this evolutionary shorthand, and there's no foresight, and obviously the plants with no brains at all don't know what they're doing. And evolution is, what we get is the product of competence without comprehension. And think a lot of competence without comprehension. This is something very important to remember. And we have it, we're loaded with it too. And we don't like to think about it, but our entire autonomic nervous system, our hearts go, speeds up, slows down, does all of this. And mine has been doing it flawlessly for 90 years, and I've never had to think about it. And the system does this. And I don't think the autonomic nervous system has any insight as to what it's doing. It's competence without comprehension. And so that is one of the major features of evolution. And with plants, it's so obvious. There can't be much competence or much comprehension in an organism that has no brain. So, having said that, I think we do have one or more mics, and we can go to the Q&A.
Sure, Rob. Others aren't aware of it.
Q&A, please.
Gordon, you've talked about the variation in the shapes of leaves. Can you address the different colors that they produce in the fall, some of them at least?
Yes, we all love the fact that in the fall, the same leaf changes color. And what is involved here, that when a plant is letting its leaves go, they have evolved to pull out of stuff that is savable, that you can pull out and store it and have it available next year. And chlorophyll is easily taken off and stored. So the plant is pulling out the chlorophyll, and what is left with all the other compounds, the colors that were there all the time but were masked by chlorophyll. They were all, those reddish and orange things, they were always there, but you couldn't see it because it was masked by chlorophyll. And those xanthophylls are hard to break down, and the plant throws them away. but it doesn't throw much chlorophyll away.
Okay, I went on a naturalist tour of Queensland up in the rainforest, and one of the naturalists said was very important for the rainforest were cyclones, because the cyclones periodically tore into the canopy and allowed the sunlight to come down on other things to grow up. So does that impede evolution because they don't have to contend with constantly with the canopy because it's torn apart periodically?
Well, one of the things I didn't emphasize was that how much wind the plant is exposed to, and I've mentioned it briefly with palms, but you have a lot of the rainforest trees, when you're down from the canopy, you never get any wind, almost nothing, so that they have no adaptation to withstand wind, so occasionally you get and throw things down, so that plants differ enormously in their resistance to wind, and those that are growing particularly in the understory of forests, it's almost always calm, so they have no ability to withstand that. So that's one area of variation that's very important, and I didn't talk about it.
Gordon,
Go ahead.
when are you going to take us on a field trip?
Is this working?
Well, let's talk about that. I have conducted field trips, mostly about birds. You know, I'm the bird guy. I haven't talked about birds at all, which has kind of got me into science in the first place, is the love of birds. But I love plants too. But we can consider the possibility of field trips. I have led many field trips, and it's negotiable.
Gordon, what got you going into grass and birds?
Well, what got me going in the first place is I got hooked on birds when I was a kid. And my dad and I bird watching. And when I was around, maybe 13 or so, I made this momentous discovery. People got paid to do this. I have just given you the long story of my search for a career. That's all there is to it. I decided I want to go to zoology bachelor's degree, got a zoology PhD degree, got a job here as a vertebrate zoologist where I could study birds. It's a winner. It's a winner. But seriously, that's all there is to it for me. Of course, then when I really got interested in biology, all of a sudden this magnificent world of variety opens up, and I'm not going to just sit there looking at birds, much though I love them. Does that answer your question?
Whenever I think of leaves, I think of if leaves be three, leave them be. Are there a lot of leaves that are poisonous?
A lot of leaves, pardon?
That are poisonous?
One of the things I did not discuss at all was defensive chemistry of plants. I mentioned it briefly that grasses are defended physically and really hard to digest. But another dimension of leaf differences that I didn't talk about because you can't show it is the amount of defensive chemistry. And so plants are heavily defended chemically in different ways because plants that are growing in environments that are short on nitrogen tend to have carbohydrate defenses. Those that are growing where there's a lot of nitrogen will have nitrogen-based defenses. It also depends on the successional plants. Plants that come in under disturbed areas and grow up fast can often get away without being fined by herbivores. Those plants tend to have much lower defenses. The plants that are growing slowly and that have plenty of time for the predators to get there, they tend to be more heavily defended. And in fact, one of the interesting questions in ecology that have been debated for a long time is, why is the world green? And that's not a question of biochemistry. Why is it that the plants are escaped being eaten down? So why is the world green? So there's a whole world of chemistry defenses. I couldn't show it, so I didn't talk about it.
At one time, we had a little field trip around Horizon House, and I believe it was the gardener, or the head of the gardening department, was telling us that these trees with the Christmas decorations, the black bumps, some of them have more, some of them have fewer of them. And the reason they have more is because they seem to be getting ready to die. So they produce a lot of seeds. And so as a result, we see more of this decoration on the tree, natural decoration.
Well, it's often true that when plants are being hit hard and about dying, they may go into a reproductive frenzy and really put out a lot of stuff just before the last chance to reproduce. And again, they're not thinking this out, of course, but there is a lot of that. And speaking of a field trip, in the spring, we could walk around through Freeway Park and I could show some things if you happen to like that. And my rates are very reasonable.
So I want to come back to the kelp. Now, when I think about a kelp forest, my kids, like everybody's kids, used to drag those leaves around on the beach. But they grow up, don't they?
Yeah.
And so they sound like the monocots, are they not?
No, they're not. They're algae. They're very simple, one cell layer thick. They don't have stems and leaves or anything like that. They have a little thing at the bottom called a holdfast, slightly variation to anchor it, but every little structure there is photosynthetic, and they're all bathed by everything, and so they can grow so rapidly because they don't have to spend any energy on support. So every cell is photosynthetic, and a big tree, you've got an awful lot of dead wood, so to speak. So that the tree pays a big price for holding leaves up in the air. And as a matter of fact, by the time a tree gets about 15 years old or something, there's no increase in the number of leaves as it gets bigger. There's just more and more goes to support the holding the leaves up. And the number of leaves is pretty constant. And what separates, what determines the height of which tree can really be adapted is how much energy is going to support system. And if you watch trees dying, you notice they die at the top. Those are the hardest leaves to support. And so that what sets the height of trees. And that's the same principle that determines the height of usable buildings. It's not the construction. We could build buildings that go even taller, but you don't get more usable space. And why is that? It's all eaten up in elevators. And so these big tall buildings that the countries compete for, in terms of providing office space or anything, it's stupid.
I have a question, Gordon.
Oh,
I have a question about magnolia leaves. They are so, they're sturdy,
yeah.
but it seems like they would block so much light from the leaves below them.
Yeah.
What's the trade-off there?
Well, magnolias are subtropical, so there's multiple leaves, but they have to withstand freezing and stuff like that, so they're tough. But they have to be tough. And the magnolias are not able to play much of the stacking stuff because the leaves are round in the same shape, top and bottom. So they're dependent on actually being where the sun is passing over and you're picking up sun at various angles. But there's no stacking like that in a magnolia.
I have two questions. Where does bamboo fit?
Okay.
Is it a mollycott?
Bamboo is a grass, so it's a monocot. And I didn't talk about bamboos because they are remarkable. But they're very simple structure, and they don't really make anything like wood. And the bamboo, like a palm, is the same diameter the whole way up. So it's a monocot. And it's the most unusual. Grasses are amazing. Grasses are really fantastic. And I have a love of grass. But anyway, second question you had?
Why are we losing some of the, what should I say? Well, I forgot the question.
Okay.
Can you talk a little bit about seaweed? Is that been related to the kelp that you spoke about earlier?
The which?
Seaweed.
Seaweed.
Seaweed. Yeah, well, they are all, what we call seaweeds, are all simple things. Kelp are just big seaweeds, yeah.
Okay.
Yeah, and a lot of them, they have a little hold fast, but they don't have any conducting systems. They don't have anything like it. They're one cell thick. So every cell is in immediate contact with the environment and picking up resources. There's no transport system. All that venation in the leaves, that's a transport system. That's moving stuff around, because the leaves are the only thing in a woody plant that are photosynthesizing. All the rest are dependent on the leaves, so you got to get the resources around, and you got to get it up to the flower. So the evolution of complex, these are called vascular plants because they have a circulatory system. None of those seaweeds have that at all. And that, interestingly, vascular plants have had almost no success in reinvading the ocean. They evolved on land, and there's seagrass in a few places, but the vascular plants have had almost no success in reinvading the ocean, whereas us vertebrates, like birds, mammals, and stuff, have reinvaded the ocean very successfully, having evolved on land. But plants, you don't win in that environment because you produce stuff that's not very helpful. Algae get along just beautifully without it.
You mentioned bamboo, and some bamboo is very invasive and others are not. Can you explain that?
I don't know enough about bamboo really to answer that question, but bamboo can be very invasive, and I had direct experience with it during the war. I went to Vietnam to look at the ecological effects of the war, and there were bamboos growing up all over the place. Bamboos are a monocot, and the Agent Orange that is used to defoliate doesn't hit monocots, so the bamboo were proliferating. And one of the reasons I went back to Vietnam much later was to see whether the forest had recuperated or were bamboo holding on, and bamboo were not preventing the reestablishment. But see, they're also tiny bamboos, but they never get big. Bamboo is highly variable. We get much interested in the big ones because we can make furniture and other stuff out of them. It's just great stuff, and it goes really rapidly, and it's good stuff. That's about all I can tell you. I'm sorry.
Gordon?
Yes.
When we moved to Skagit County, one of the first things I did was start trying to learn to identify native plants. And on one field trip, we went to a nearby park area that had a lot of natives. And the guide was telling us, you know, different things about leaves and the structure of the plant and how this is this and this is that. And we came to one plant and he said, oh, I'm just not even going to talk about that. Which of course made me very curious. You can't just walk by a plant and say, I'm not going to talk about that one. But it turned out that I'm thinking it was snowberry, and I could be wrong. But its leaves, like it has lots of leaf designs. Some of them are nice and smooth, some of them have little scallops, some of them have other. It's very inconsistent, even on one plant. So it turns out it's actually a challenge when you come up to a snowberry to know what it is. And how can a plant species produce such different kinds of leaves?
I think the answer is the same one I gave you for the oak leaves. the kind of leaf that develops relates to the wind and sun that's hitting the leaf as the time it's opening. And that can give you a lot of variability within a plant. And I think that's primarily what's involved in snowberry as well, the different leaves on the same plant or different plants growing in very different circumstances, the amount of sunlight hitting the leaf and the leaf expands can affect exactly how it comes out. And snowberry is also interesting too. The berries are eaten by birds, but they get better after they're frozen, which is probably an adaptation to keep the berry on the plant through much of the winter, where it's less likely to be eaten by rodents than if it's dropped to the floor. So snowberry berries, and snowberry is a honeysuckle, by the way, it's a honeysuckle family. That this change in the palatability of the berries affected by freezing is probably adapted to keep. It's better to keep the berry up on the plant rather than on the ground during the rest of the winter. Does that help you?
Any other questions?
Can you talk about which trees are surviving in drought areas?
Speak a little louder, please.
Which trees are equipped to survive in the new drought areas?
Well, one of the big problems now for trees is the climate is changing, and many trees are growing under circumstances where it's going to be hard. And the big thing is that's the reproduction. And there's a lot of areas now where it's getting drier or something. And if you log a forest, the same trees aren't going to come back because the climate differences are very, very important when you're regenerating them young and having to compete and get started. And that's the big problem with changing, is that really some foresters here think that a lot of the forest trees, the conifers here, where they're common in places now, if we cut them down, they won't come back because the germination conditions are so bad for them. So it's a big problem for trees, and we may end up getting into the business of moving them, to keep up. That may be a part of the strategy we need to evolve to keep the trees going. It's not a pleasant thought, but maybe what it's going to take.
Surely in forests we will just plant with a different species.
Yeah, I mean, it's going to change, and then it's a decision. If we lose the conifers and something else comes in, do we care? And that becomes a different sort of societal problem that isn't entirely, it's much more than just the ecology part of it.
But forests are farms, so the manager of the farm is going to decide what they're going to put there.
Yeah. That's going to involve, we may have major decisions. What do we replant with? This is going to be one of the major societal decisions that we're going to encounter as we deal with the changing climate. We're adding to our problems.
Gordon, this has been terrific, highly informative, and once again, who knew?